Why are you doing this class? You definitely have some reasons because you already invested like half of semester. So much fun. Okay. So you didn't update it. Okay. It's fine.
Oh, I'm sorry.
So what is so funny in this class? What is important? And what is the connection to your other courses or career plans? Looks like a fixed puzzle. If there was no reason to stay in the class, where you stay? So what is there any class that has connection to this class? I know that you there is a logic in taking calculus and differential equations in order to take this class. Is this class a prerequisite for anything?
It's too.
Oh, okay. Okay, so Alex may want to take physical chemistry too, and therefore take it. Yeah. Yes. Who's taking inorganic? Who you taking inorganic? Okay, now I see there is a reason. You just either keeping secrets or being or disclosing. So, and what are you doing towards inorganic? Not yet? Nothing? What is the subject of the next chapter? Yes, you can just read it instead of scrolling through the menus. Where did you start? I'm curious. So what is oscillating? What is oscillating in the life of physical chemistry? Examples. What kind of oscillating either in regular life or in science?
Sine and cosine function.
I am in presence of highly educated mathematicians. But what in natural sciences? And what else? Sound, okay. Like compressions and decompressions. Yes. What else? This is really good. Okay. Intensity of electric field. Okay. Gravitational waves of this. Okay. What else? This all will be physics, acoustics, electrodynamics. What is oscillating in chemistry?
You had a reaction that was close to 0 on the delta G scale. It could oscillate back and forth between equilibriums.
Reaction. Yes, there are reactions that oscillate, but something much more common and natural. Electron, it does some periodic motions. They are not always oscillations, but yeah, not bad. But even, I cannot say more common, but as common as electron. What are you dealing with as chemists? Atoms, molecules. So what atoms are you? If there is no reaction? Huh? Yes. So even if electrons are stable and do not go anywhere, but if you heat material, the atoms start to move. And if there is no reaction or dissociation, they just oscillate around the atomic quantity, equilibrium distance. Okay, so the main goal for next lectures is to see how atoms are oscillating, and later on there will be some consequences for observables that may pop up in the instrumental measurements, which we are not doing in this course, but later on you may be exposed to infrared spectroscopy. Okay, now the super question. What do you remember from last lecture?
Doing matter operators.
Huh?
We're doing matter operators.
Oh, good. Who remembers anything about it? Who remembers the name of the weather operators? Alex may be excused from reading the weather. Just the answer. Well, I see that you remember that somewhere in the notes there is something about weather operators. It's already a progress. But what is a standard protocol to explore any new model, any new object in our class? Which techniques can this time? You remember the navigation slide with different methods and different objects, right? Do you? So which methods do you remember? And often the methods accumulate on the top of each other. You cannot go further before you do something really basic. Which equations do we solve? Okay. Which two types of Schrödinger equation do you? And which one is easier?
Independent.
Good. So we do not need to talk about anything more advanced before we solve time-independent Schrödinger equation for a new model, right? So we need to solve time-independent Schrödinger equation for harmonic oscillator, which represents interatomic bonds. The simplest example is H2 molecule, right? Where hydrogens oscillate near each other. And where this equation comes from? What is it?
Taylor series, right?
Huh?
The Taylor series?
For which term Taylor series helped us? What is shown here, and what do we see, and what do we do? Do we need a Taylor series for the first term? Did we ever need it? So what is first term?
Kinetic part.
Yes, it's kinetic energy. I can't write my finger on here, but probably. So kinetic energy. Then what is this? Yes, potential energy. And for potential energy, we did practice expansion around the equilibrium, right? So it was position at equilibrium plus first derivative times deviation from equilibrium plus second derivative times deviation from equilibrium squared. And we can do manipulations to forget about the first terms and have only the left. Our square term is potential energy, right? If you depart from equilibrium, energy increases. So what is this phi of phi? Do we know it? Or do you remember what? Do you remember how phi of r equals to something? It's a simple setup. If you declare that you do not know it, then it is our unknown function, right? Which we need to find. We want to know it, but we do not know it yet. And energy is also unknown, right? So it is time-independent Schrödinger equation for this case, right? So who can solve this equation?
Probably.
Okay, that's for me who wants to solve this equation. Then we can get answer that no one. Well, we have to. It is a substantial effort that we have to do, but it is not pleasant and not easy. Why did we started to talk about weather operator? What is it?
I remember you said it was easier than calculating out things before.
Yes. So there is a standard way to solve this equation through expansion in series, and it is really hard. And weather operator is like, about 10 times easier, although it is also some effort. So why this equation is complicated?
This is a second order differential equation.
Well, we successfully solved the second order differential equation when we had zero potential. There were sign for this place. So this term with non-zero potential and this potential continuously changing is bringing additional challenge. Without this term, one would just plug in exponential and see what happens to coefficients. But here the answer is neither exponential nor sine nor cosine nor polynomial. So how many solutions? Typical quantum equation has. Yes. So it will be more than one answers to one equation. So several functions and several energies. Okay. Can you go downstairs lower than basement? So that's the main idea. So if we assume that we already have a set of wave functions, first set, zeros, first, second, and energies for them, then the trick is, so it is standard, it is legitimate. I'm not giving you something insane, but it is second in the list of stuff. I'm skipping most mathematically hard stuff. So assuming that we know these functions, we can hypothesize that we can design abstract mathematical operator that will correspond to walking the stairs up or down, only one step at a time. So if we are in ground state, we go up by this raising operator to the first step. If you apply this operator once again, we go to the second. If you apply it once again, so and opposite, if you have lower an operator, we just climb down. And the main idea, main benefit, immediate benefit of this hypothesis, if we will be successful, is that by applying lower an operator to the lowest possible state, we should get what?
Zero.
Right. Is it convincing? Okay. So if we design in the right way these weather operators, then we will need to solve a situation like this. This weather operator, which also may include some differential stuff, acting on a known wave function from wave function, will give 0. There are good expectations that this equation will be so much simpler to solve than the Schrödinger equation. But if we would already know the raising operators, so we first find lower state, then we apply raising operator and climb up and generate excited states. So it will be easier and it will be more close to natural science. We will not devote like 3 lectures to pure math. We will do a little bit of math, a little bit of analysis, so that we understand what we are doing. Okay. So, how to design these operators? If you are busy or if you need to relax after the relaxation on weekend, you can fall asleep. I will give you a signal. Oh, someone literally followed me. Like, okay. I will give you a sign when to wake up and when to concentrate substantially. Right now, it will be some auxiliary information. It's useful, but not like top cream of the cream. So I'm not going to give a very rigorous mathematical source for this weather operators. And we do not have much power, much skills, and much objects in this area. The operations that we can successfully complete are limited by now. So we do know Hamiltonian. It is a plus. We do know that there are some fundamental basic operators like position and momentum. And we do know that Hamiltonian can be expressed in terms of position and momentum. Right? Which is here. So instead of differential operator for momentum, you can just put E squared equal to kinetic energy, and this mass frequency squared equal to elongation squared as a position squared. Right? So Hamiltonian is expressed in terms of position and momentum. So there is a hypothesis which is not supported by anything right now. It's like an idea which is not yet proved or supported is referred to as hypothesis. So what if we add together, we build a superposition of position and momentum operator, just add them together, and check whether some values of coefficients, like hitting in front of position and momentum, will give what we want. So it keeps is not super important. In about 15 minutes, when I will declare the values of these coefficients, it will be time to focus and to record. Right now, it is just logical. Okay, so the abbreviations here, P1, P2 is for plus, and M for maybe minus. It's plus if you go up, minus if you go down. Make sense? You always need to design some abbreviations. And then there is a really interesting and important property that comes not from formal mathematical derivations, but just philosophical. Suppose that you already have this operator. It allows you to jump from one eigenstate to another one, up or down. Now, if you have a quantum system that, let's say, sits at state number 1, right? Then you apply lowering operator, and after you apply raising operator. What will happen to the system?
One still.
Yes. So it's really cool. So if you apply a combination of raising and lowering operators, you will return back to the state where you started from. And there is another hypothetical statement that later on will become very natural. We'll prove it later. Then by in harmonic oscillator, the energy, the Hamiltonian, can be referred to as index of the state multiplied by a constant. So based on this not very rigorous, not very strict, like fluffy ideas, one can formulate a plan how to design this ladder operators. So if we would multiply raising and lowering by itself, raising operator times lowering operator, we should obtain Hamiltonian back. We should obtain this r squared, p squared with right coefficients. So the procedure to find this ladder operators would be assume this functional form, opposite proposition, then multiply them one by another, and make a match, make a solve this equation for values of coefficients. So on one hand, we will have this product of raising and lowering with unknown coefficient. On another hand, we will have this p squared and then r squared. So if raising and lowering operators are linear in p and r, then maximum power will be squared second, right? And we see that there is no first power in Hamiltonian. It's only proportional to either position square or momentum square, which means that there will be some cancellations. If you open bracket, the terms that you have products of PR and RP should cancel each other. Okay. You can, those who are not sleeping can get tired or irritated, but I promise what I'm doing is easy. So, thing number 3. If we are doing games, if you're playing with good wave functions, they're normalized. If you're playing with good operators, they should be Hermitian. So another piece of hypothetical input is that if we do Hermitian conjugation of raising operator, it will convert into lowering operator. If we apply Hermitian conjugation to lowering operator, it will convert to raising operator. So if we bring in this hypothesis number 3, so total 3 hypotheses were that our raising and lowering are linear in position of momentum. Second, that their product will give Hamiltonian. Third, that they're Hermitian. If you stick all this in, one can solve and find the coefficients and declare these operators. So there are not too many ways to do linear combination. We can put plus here and there and just assume that this coefficient is will include them as well. 4 unknown coefficients. P1, P2, P1, P2. And by opening this bracket, we should get this equation. Keep sleeping. I will wake you up when there will be a solution. So if we are opening the bracket, there will be square terms, there will be cross terms, and note that in cross terms, the order of RP and PR will be different. You already know that quantum operators do not commute. If you solve the order, there is a penalty. So if we do it, P1 and 1, it should be the same coefficient as P1 in front of Heineken T square H bar square over theta. And then because of the Hermitian property, it will be just T1 times T1 star and equals to minus H bar square over L, which means to find this T coefficient, we just take square root of this factor in front of this factor H bar square root of L. If you're looking for the coefficient that will pop up in front of quadratic term, will be m omega square over 2. We need to take square root of it. And then, in order to process the cross terms, one needs to deal with fact that if you swap them, there is a penalty. And if we carefully follow the steps, one would obtain the values for the wake up if you were relaxing. So this is object that we will practice, that we will use again and again for a couple of weeks for sure. And there will be some homeworks based on these objects. So it is not a bad idea to write down and remember. So raising and lowering operators can be formulated as superposition of position and momentum with coefficients that are obtained by matching of product of the ladder operators and Hamiltonian. And this is often missed in textbooks. I just gave this little guidelines to have the logical picture and to help all of us to memorize. I cannot brag that if I wake up in the middle of the night, I will remember this coefficient. The only way is to either look into the cheat sheet or to read the write. But how can we characterize for, maybe not for immediate memorization, but just get acquainted with these two definitions? So, Hermitian property. Here in front of R, everything is real. Real is always Hermitian. In front of momentum, the coefficient is imaginary, with plus and minus or lowering and raising. Which means if we apply Hermitian conjugation, complex conjugation, the sign in front of imaginary unit will flip. Right? So we immediately see that these two operators match the requirement of, they are Hermitian conjugates of each other. Right? Make sense? What else? They both, interesting that for lowering it is plus, for raising it is minus, which is, so if you see dagger here, it will be minus here. Both coefficients do have square root. The square root originates from matching between terms in Hamiltonian and this special coefficients. In both coefficients, the constant is in denominator. 1 over 2 bar is in denominator here and there. Both coefficients have square roots. But in the one in front of position, we have square root of mass and frequency in the denominator, and in the coefficient in front of momentum, we have square root of mass and frequency in the denominator. Why were we doing this? what did we declare before planning to go asleep? I'll try to remember. So we are starting oscillations. For oscillatory motion, we formulate Schrödinger equation. First time-independent Schrödinger equation. And by your and our common mathematical intuition, we recognize that this equation will be not easy to solve. Therefore, we decided to go over the bypass shortcut. So these ladder operators are expected to help us to solve time-independent Schrödinger equation with much less mathematical efforts. Later on, they will bring a lot of another benefits, but the first immediate benefit is speed up in solving time-independent Schrödinger equation. So what did we promise to each other, or you didn't promise anything to me? What did I promise?
That this would be easier.
Yes. What we are doing is super easy. Trust me. But more practical. Which steps will be especially easy? What will we do instead of literally solving time independent Schrödinger equation?
Apply these to function that, or apply these to a wave function that's at a certain excited state, and then it would either go up or down excited state.
Excellent. But it is too general. There is a plan. We will start of deriving wave function for ground state. And then as soon as we have ground state, we will apply raising operator and generate first excited, second excited, and so forth. But first we need to get ground state. How are we going to get it? Scroll through your numbers. 20 minutes ago. Trying to go down to basement and then going lower than basement. Yes, if we apply lowering operator to lowest possible quantum state, the result will not give us new quantum state. It will be just zero because this operation is not possible. Okay? So we are going to apply this lowering operator A to unknown ground state wave function and philosophically assume that it will be zero. So solving this equation is much, it's like 20, 50 times quicker than solving actual Schrödinger equation. So you'll just plug in this stuff into this equation and try to solve it.
Before we move on, M equals mass, W equals angular momentum, correct?
No momentum, angular frequency. So potential energy is K R square over 2, where R is elasticity, right? And this elasticity constant can be replaced by mass times frequency squared. But frequency is like how often it oscillates force and back. So we do plug in definition of momentum operator, which I have moral right to ask you to remember it because I remember it myself. And probably you already do, right? So it's minus IH bar derivative over position. And then we are getting an equation that has some coefficient times position, some coefficient times derivative, multiplied by a known function. R times unknown function phi plus d phi dr equals 0. Well, I'm skipping coefficients, but just checking that this equation doesn't scare you. So there are no second order derivatives, and there are no squares of independent variable. So this one should be solvable, right? Okay, let's scroll back. Or R phi plus T phi dr equals 0. You can bring derivative to the right side. R phi equals d phi dr. So now we can move the divide both sides by independent variable and multiply both sides by no, wait. Divide both sides by wave function and multiply both sides by increment of variable. So RdR on the left and d phi over phi on the right.
Would it be
With minus. Yeah. No chance for extra credit to that. Okay, makes sense. And then both you can put integration sign on both sides. What is integral of linear function?
pi squared over 2?
Yeah. What is integral of 1 over pi?
Negative natural log of pi.
Good. And then you just do some manipulations to prepare it more appetizing form. Solve for phi.
We go back, like, where did we get R5 plus D phi dl? How did we go from that top equation to this?
Really? Who else supported this question? Thank you so much. Stop me more quicker, because we can think on different places. Some things that can be evident for you can be very hard for me, and I can mumble for half an hour. And some things that I assume natural could be requiring additional comments. So we are multiplying both terms onto a known function. So we are opening brackets. Right? Then we have all these boring constants. R times phi. Plus boring constants I, H bar, square root, and then DDR times phi equals 0. So we have R times phi and DDR times phi. In the next equation, I just skip the constants. Otherwise they distract the attention. But we need to work on constants and make sure that they are not forgotten. Just first we make sure that the equation is solvable in principle, and then we work out all details. Thanks much for pointing to that question. Okay. So the constants, if they're taken care of, will be just one over each part, and the rest is effective before. And if we integrate both parts, in integration of 1 over another function with the logarithm, integration of the r with the r squared over 2. And if we plug it in, we may want to put left and right parts into the powers of exponential, right? Why? Because we need to solve for wave function. So we put the answer on the left side of the differential equation in the power of exponential, since we want to get pi. And same thing for the results of integration on the right side. What is exponential of logarithm? Correct. So we do have, and I messed up the notations, but let's rename this unknown coefficient c into the letter n because it is the normalization constant, which we need to work on later. I'm not sure if today we will have time for this, but wave function of ground state developed under assumption that weather operators work and that one cannot go lower than ground state, gives you a function that you may recognize. On money of which country the designer of this function was shown?
Germany.
What's the name of the guy? Yeah, Gaussian function, right? You recognize it. Exponential to minus independent variable square. And this another stuff that comes here determines the width. So this constant mass. This is not mass of electron right now. We are talking about atoms. It is either mass of an atom, also called reduced mass. Special equation for average between if you have hydrochloric 35 times different than mass, reduced mass. Let's see of oscillations which can be measured from plasma. Notice this factor 2 that originates from integration. So if we are going to large objects with huge mass, then the width will be super narrow so that we can forget about quantum effects. And if we are speaking this about light, atomic and molecular objects, the width is substantial. So this is one of the manifestations of quantum nature of atoms. Although we know the equilibrium distance, even at zero temperature, there is a little uncertainty where atoms are. There is a chance, there is a probability that they're a little closer than equilibrium distance and a little further than equilibrium distance, according to Gaussian distribution. Good. Try to make some records by your own words. This is something. It sounds trivial, but it's one of the main take-home messages of the course. Change those 2 minutes. So the next step function looks like Gaussian. similar to ground state of particle in the box. There is one peak in the center, but it never goes to zero. It decays very smoothly. So longer elongations or contractions are possible, but their probability is vanishing. So we are kind of done with this stuff. I want to give heads up for next steps, because we need to go forward that crazy. So next step when we meet again will be to find out the value of normalization coefficient. Although we already know the functional form of ground state, we are not aware, we do not know what is the normalization constant. And sometimes we will need literal thing. So we will need to multiply the function conjugated by itself, integrate, and make sure that result is equal 1. So this will solve it. Okay, done for today. Looking forward to see you on Wednesday. We didn't have enough knowledge about new subject to do any homework, so we just accumulate strengths.
So Dimitri, over the weekend I saw this article of a team who got something like a set of atoms to go below 0 Kelvin.
No, do fake news.
But they said it was done by freezing the atomic spin because at 0. Would that be true if you?
No, it's.
I corrected it.
Oh, okay.
Reading it on the onion.
No.
There, it is not possible to go to negative temperature, but there are some effects, some processes that would look as if temperature is negative. For example, if you have a laser pointer or laser in the lab, there is a so-called inverse equation when the electron from highest occupied orbital is transferred to lowest unoccupied. Okay? So it is inverse occupation. It will not exist at a long time. It will relax. It will go back with emitting of photon. Right? There are theorems from PCHEM2 from statistical mechanics that in equilibrium, the occupation of electrons depends on temperature. At 0 temperature, it will be just all occupied orbitals are occupied, all unoccupied are empty. And if you increase temperature, there is a thermal excitation. There is a little less on the occupied and a little more than 0 on unoccupied. At infinite temperature, it will be like 50-50, everything will be occupied. But there is no positive temperature that will give you more occupation in the originally empty. There is no such temperature that would give you inverse occupation as in lasers. But if you mathematically assume that temperature equals negative value, then you will naturally, and plug it into distribution, you will get inverse occupation. Therefore, you can tell that laser is a matter of negative temperature, which is not right. If you put in thermometer, it will be right. So, if it is discussion on this lines, I would agree. But not every article is correct.
Oh. that's why I brought it up, because I was like, I don't think that's possible. But they said the team was trying to freeze the spins of freeze the vibrations of atomic particles. That if it was frozen, since they're not vibrating and you have vibration at 0 Kelvin, it would technically be negative.
Can you send me the link?
I'll see if I can find it again.
Okay.